Dzień dobry Państwu. Czy jestem słyszany w Zoomie?
Tak. Tak.
Ryszardzie, chciałem zapytać, czy są obecni recenzenci?
Już sprawdzam. Kasia Małek jest obecna.
Tak, jestem.
Natomiast nie widzę nadal drugiego recenzenta. W takiej sytuacji prawdopodobnie będziesz musiał odczytać jego recenzję,
tak,
jeżeli recenzent się nie pojawi.
Wymagane.
Okej.
Może maila posłać.
Tu wysyłane zaproszenie, także nie było odpowiedzi, co prawda, na to zaproszenie.
Przypomnienie, no to zróbmy przypomnienie, żeby już, że tak powiem, wywiązać się.
Dobra.
Rozumiem, to znaczy możemy
rozpoczynać, a my z Leszkiem to uzgodnimy.
Założymy, że nie dołączy.
Dobrze. Dobrze, jeżeli się nie pojawi, to odczytamy jego recenzję w całości. Dzień dobry Państwu. Witam na publicznej obronie rozprawy doktorskiej magistra inżyniera Filipa Morawskiego. I would like to welcome everybody to the public defense of Filip Morawski. His thesis is titled Applications of Machine Learning Methods in Gravitational Wave Detectors Data Analysis. The advisors for the thesis are Dr. habilitowany Michał Bejger of CAMK and Dr. Elena Kuoko of the European Gravitational Observatory. Elena, I think you are there. Welcome.
Hi, welcome.
Okay. And we will begin by a presentation of the candidate by Michał Bejger. Okay, thank you very much. I hope you can see me. Where should I look? There, okay. So I will first present my point of view, and then I will give the voice to Elena, who will present the, let's say, second part, because it's very nice that this PhD thesis was split kind of neatly into two halves. We worked together on this. So let me, I will try to summarize my statement. I will just first say that we started to collaborate in the middle of 2017, just after Mr. Morawski finished his studies in technical physics at the university, AGH University of Science and Technology. And we already knew about Mr. Morawski at CAMK because he was a summer student in the previous year, so he was already known as a prospective student. So I was very happy when he joined the project. And so the project was the Sonata BIS grant. It was devoted to the development of theoretical models and data analysis based on machine learning, which is basically exactly the title. And we also, started to this work in the framework of LIGO-Virgo collaboration. So this also worked quite well, in my opinion, because despite or maybe thanks to the slightly different education than the traditional astronomical curriculum that usually students in Copernicus Center have, Mr. Morawski basically out of the door started to implement the things without any problems. I have to say here that his ability to organize his work and produce results are very impressive, I have to say. So at the same time, we have also started the European COST project, G2Net, a network for gravitational waves, geophysics, and machine learning, which resulted in this collaboration with Professor Elena Cuoco, who became the co-advisor, and well, she will tell about the projects, I hope. And towards the end of the PhD, Mr. Morawski won the NCN Preludium Grant and Wilhelmina Iwanowska-Nawa Fellowship for a pre-doctoral internship at the University of Glasgow in the LIGO group of Professor X. Yong Heng and Professor Chris Messenger, who are conducting groundbreaking research at the interface of machine learning and gravitational wave data analysis. I think it's a very good choice of the group, and I already saw some results, very prospective results. In the meantime, Mr. Morawski was very active in popularization of science, organization of scientific conferences, hackathons, preparing data for exercises and mock data challenges. That was a part of the COST action. So all in all, a lot of work that is not really included into this PhD thesis. At the time of writing this text, Mr. Morawski has co-authored approximately 70 papers, mainly through the collaboration in LIGO Virgo collaboration that is cited 5,000 times, the H-index 25. But his PhD thesis consists of 4 short author-list publications discussing different directions of gravitational wave data analysis using machine learning methods. Basically, the topics are what we thought are fundamental questions that have to be asked in this regard. So the topics have been selected to simultaneously review different types of gravitational waves and their sources, continuous waves of rotating neutron stars, transient signals from supernova explosions and spiraling binaries, but also data analysis applications. So this is basically signal detection, but also signal classification, parameter estimation, and reconstruction of the signal, and data analysis methods, so supervised and unsupervised learning methods using neural networks. And so far, these papers are cited over 30 times. So just a few words about the thesis. So the thesis is, as you will see, is divided into several parts, which basically we kind of, Mr. Morawski entitled kind of, let's say, not entirely, how to say, seriously, just a kind of a joke. The parts are basically the expect the unexpected, which is basically a quote from Oscar Wilde. And you will see this is about anomaly detection in gravitational waves, things that are maybe there but are rare and not the usual. Then there will be a part about troubling signals. So the part is titled "Trouble is My Business," which is a quote from Raymond Chandler, detective story of Philip Nomen Omen Marlowe. So this is about difficult signals that are difficult to model or very weak, and which nevertheless we would like to discover in the gravitational data. And then the third part is about inferring information from the data itself. So this is about the relationship between the input and the output. This is demonstrated on the reconstructing of equation of state using, performing in some sense, an inverse of Tolman-Oppenheimer-Volkoff equations. So I will conclude here that basically all these topics are at the front of this field of work, and they have many following steps. I mean, all the directions are open, and we can continue in many of them. Basically, we'll conclude to say that this, in my opinion, shows that Mr. Morawski showed quite a huge scientific potential in performing various tasks in the PhD thesis. So thank you very much, and I will give the stage to Elena.
Yes, Dr. Kouako, would you like to add something?
Hi, everyone. I want to add a few more words to what also Mayol said. So I met Mr. Morawski in 2018 when he came in Pisa as a visiting student at Scuola Normale Superiore. And I was really impressed by his skills, his attitude to work with us. He was every time really proactive in the project. He was able to deal with many projects at the same time. It was really nice for the people in the group to work with him. He acted also as a tutor with the younger students, the internship that we have, and was able to follow their work. Then I have to say that I can consider Mr. Morawski as really a pillar of our group because he supports many works that we did in these years. We work mainly together on the machine learning application to the data analysis for the search of this kind of signal that Professor Beiger described, and in particular to the disentangle of the noise and the astrophysical signal from gravitational waves from transient signal, so CBC, spiral binaries or core collapse supernova. And he was really very active. We produced few paper, very good paper, with his help. And he was able also to work in the innovative environment for the software production, and always available to help. And this is really a good attitude that I want to underline, and I think that Mr. Morawski could be a really great researcher. Thank you, and good luck.
Thank you. Okay, so now it's time for Philip to present the main results of his PhD thesis.
Okay, can you hear me? Yes, I guess so. So thank you very much. Hello to everyone. Good morning to all of you. So today I would like to present you the research I did for the last couple of years that at the end constituted to my thesis. And as you heard, it's about the application of machine learning methods in the gravitational wave detectors data analysis. So does it work? Oh, technical issue. Oh, okay. It works now. Good. So what are gravitational waves? So, well, when discussing gravitational waves, we usually have to go first to the general theory of relativity. So according to this theory, objects curve space-time around them. The more massive the object is, the larger the curvature. So what happens when those objects start to move is that the curvature of space-time around them starts to change. And when the motion is an accelerated motion, then the changes in this curvature start to fluctuate. And thus, the gravitational wave is born and it propagates outward from the source of this accelerated motion. So there are quite a few similarities that gravitational waves share with the electromagnetic waves that makes a bit easier the understanding and studies. So first and foremost, they both transport energy. They have the same speed of propagation, which is equal to the speed of light. They have two polarization states, as well as they are described by similar wave equations, which, yeah, indeed, it makes it a bit easier to, let's say, study from the numerical point of view. But as for the differences, then the obvious difference is the one associated with the fundamental forces in nature that those waves are associated with. So we have electromagnetic forces as well as gravitational forces. The main difference between them is their strength. So electromagnetic forces, since they interact with matter to a much, much more significant extent, they, for example, do not allow us to study the interiors of objects because, for example, in case of stars, what you usually see, at least directly, is the surface of the last scattering, whereas gravitational waves, in principle, might allow us to probe those objects. They also, when traveling throughout the space, they don't really interact with matter to a significant extent, which means that when we measure the signal of the gravitational wave, we are actually, let's say, extracting the information more or less to the same extent as it was produced. A nice way to think about gravitational waves is to consider them as a second sense that we have to interact with the universe, where electromagnetic waves allow us to see the world, the outer world. The gravitational waves allow us to hear it. So how one can detect gravitational waves? Well, the detection principle is associated with the effect that the gravitational wave has on the space-time itself. So by tidal gravitational forces, they're basically stretching and squeezing everything on their path. So the distances between, for example, like test particles that you can see here on this ring of test particles, in one direction are squeezed, another one stretched. So in principle, we can use this detection, let's say, principle in order to design certain experiment that allow actual detection. So the experiment that allowed us and is still allowing us to detect new events is the interferometer, laser interferometer, which already is quite an old concept that dates back to 19th century, where Michelson and Morley used this device to study the luminous sphere's ether, or as more popularly known, the speed of light. So what happens like at the interferometer? So basically we have a laser that shoots the beam of light that's being split into two usually perpendicular arms. The light is stored there in the so-called light storage arms, at the ends of which we have test masses, so basically mirrors. One of them is semi-transparent to actually allow the light to pass through and from the beam splitter and then back again to the photodetector. Within the light storage arm, the light can bounce hundreds of times, effectively increasing the length of the interferometers. And why is that important? Well, first and foremost, the gravitational wave, when we detect them here, like on the terrestrial experiments, they're really, really weak. For example, in case of the very first detected gravitational wave event, which is this GW150914, which was already almost 7 years ago, the deformation on the distance of 4 kilometers was just equal to 10 to the power minus 18 meter, super small subnuclear value. So that's why the interferometers we use are first and foremost large. So LIGO or Virgo interferometers have arms of like 3 or 4 kilometers length, but the effective length that the light travels within those arms is even longer. And actually, this ratio between the relative, let's say, deformation in distance to the distance itself that we call strain is an actual value that's measured at the interferometer. So yeah, since those devices are supposed to be sensitive enough to pick up such a subtle deformation in spacetime, then they're basically picking up all, let's say, noise sources that we are not usually even aware that they exist. Like, for example, gravity gradient noise, which is caused by the gradient in local gravitational fields, for example, caused by the pressure changes in the atmosphere. So this noise, which is persistent, usually dominates the sensitivity of the detector below 1 Hertz. That's why you can see this like a sharp peak on this side. And to basically remove this effect, we have to go to space. That's why we have like this idea behind LISA, so laser interferometer space antenna, to be sent to the space in the next 10 or 20 years to go to lower frequency. So then we have also the seismic noise. Well, we know that the crust of the earth shakes, but it's basically shaking all the time, even now. But we usually don't feel it. But those interferometers are sensitive enough to actually be affected by this noise. There is also thermal noise. Since majority of the interferometer operating nowadays are operating in the room temperature, the atoms constituting those test masses, the mirrors, are vibrating. And that's also causing a certain noise that those devices are susceptible to. So there is also a shot noise, which is associated with the laser light itself. So when the photons arrive at the photodetector, they do so in random times, which might cause certain interferometric fringes as well. So they're also warming up the mirrors, and actually shot noise is associated with another this kind of peak on the other side of the sensitivity curve of all the interferometers that are on the ground. So yeah, we can distinguish quite a few different sources of gravitational waves that we either expect to detect now or in the near future, because then our, let's say, interferometers will be sensitive enough to pick up those signals from the noise. So first and foremost, we have binary system mergers. So sources that we were already able to detect in dozens of events. So usually mergers of binary black hole systems or binary neutron stars or a mixed pair. In this case, we know the waveform, the signals are transient in terms of the sensitivity range of the detectors, which makes them a little bit easier to search for in the data. Also collapsing stars. So for example, core collapse supernova explosions are supposed to emit certain gravitational waves as a result of, let's say, broken spherical symmetry, which is also, let's say, an alternative mechanism that's supposed to cause the gravitational radiation. In this case, we don't know really the waveform, though the signal is transient. So in principle, we might be able to detect it with certain methods. Non-axisymmetric neutron stars. So again, yeah, this as in case of collapsing stars, similar criterion is met in order to allow for the gravitational emission. In case of neutron stars, you might have on the surface certain deformations like some lumps or mountains. Also, the presence of the companion in principle might, let's say, distort this, the surface, which might again cause the gravitational wave emission. In this case, we expect that the signal is persistent for very long periods of time. And yeah, depending on the model, we know the waveform. So again, certain approaches in the data analysis can be applied to this case. And there is also a stochastic background, which is kind of a similar thing to the cosmic microwave background, radiation. So like a leftover after the early universe, mergers of primordial black holes, mergers of very distant, let's say, black hole mergers that are too distant from us to be distinguished as a, let's say, single separate event. In this case, because of this plethora of noises, potential sources, we don't really know how the waveform might look like. But we expect that the signal should be persistent, as in the case of the background noise. And obviously, we don't know what we don't know. Like the future of gravitational wave astronomy might bring us sources of gravitational waves that we don't actually expect at this moment. Maybe dark matter, in some ways, is also emitting gravitational waves. Who knows? As for the methods, let's say classical methods that are currently used in searches, we can distinguish, let's say, basically three types. First and foremost, match filtering, which is a quite well-known signal processing method, allowing you to search for even very weak signals in the noise-dominated data, as long as you know the exact waveform you are looking for. In case of gravitational wave searches, we need like a whole bank of templates covering quite in details broad parametric space. For example, in case of binary black hole mergers, like the range of masses, spins, potentially charges as well. So yeah, excessive power methods. So when you don't know the waveform, or you don't need to, or you know, but you don't need to, let's say, utilize this knowledge, you can use this approach by studying usually time frequency maps, like spectrograms, between multiple detectors in a certain time window, and look for an excessive power stored by the astrophysical signal. Because most likely only astrophysical signal should appear in basically the same time at various places on our planet, with a very small time shifts associated with the sky position. So there is also like the cross correlation, where you can study again multiple detectors and search for similarity, for certain causality between the data found there. So all those methods have certain limitations, usually associated with quite significant requirement for quite significant computational power. And they also are prone to the presence of glitches. So since the detectors are sensitive enough to pick up all those, let's say, persistent noise sources, they're also sensitive enough to pick up certain transient noise sources that we call glitches. They might sometimes mimic astrophysical signals or hinder the actual detection, reduce overall quality of data. So it's really important to study them to understand what's actually happening in the detector. And yeah, ideally remove them from the data, which is often non-trivial because more often than not, we don't really know where those signals originate from. And there are like many different classes. Like here you can see just 4 of them, but in reality you have much more to deal with. So an alternative approach to those classical methods that might solve at least some of the limitations that the other methods have might be machine learning, which is a field of artificial intelligence associated with certain algorithms that learn from the data without the need of being pre-programmed. So usually we can distinguish, let's say, a few paradigms within machine learning associated with the data you have or the problems you face. So we have a domain of supervised learning where we have a certain labeled data. In this case, usually we're working with classification or regression problems. For example, you'd like to create a model that's capable of classifying galaxies according to their morphological classes based on images. First, we need certain data that's, let's say, labeled by us manually, so the model can learn those features from those images in order to generalize toward unknown samples in the future. Unsupervised learning. So in that case, we don't need to actually do anything with our data. We just hope that the algorithm we are using is able to pick up certain clusters of similarities in the data we have in order to do, for example, or solve the clustering problems. There is also reinforcement learning, quite rarely used, at least for now, in sciences, which is kind of like a game. So we have like the machine learning model that's learning, but not from the data, but rather by the interaction with the environment, following certain rules, rewards, penalties. So yes, indeed, it's like a game-like problem. Yeah, many algorithms exist nowadays associated with all of those domains I mentioned before. But the one that I believe attracts the most attention, and also the one that I decided to use in my thesis, are artificial neural networks. So as the name suggests, that's an algorithm that's inspired by actual biological neural network. And let's say the concept of the very first artificial neuron called perceptron, it's already quite old because it has like 60 or 70 years. So the idea was the following: to have a certain vector of inputs that would have a weighted connections with centrally located node, where this weighted inputs would be summed, and if the value of this operation would exceed a predefined threshold, sometimes also called bias, then the signal was propagating or processed further. If not, then the signal was in a sense lost by this particular perceptron. At some point, to add a nonlinear character to the perceptron, an activation function was used that was actually applied on the results of this weighted sum of inputs. So in principle, you could take the perceptron and create like a sophisticated layered structure, creating your very first artificial neural networks. Though modern artificial neural networks are obviously much more sophisticated than those, let's say, older versions. So among the most popular are convolutional neural networks and recurrent neural networks associated, let's say, with different problems we are facing in data analysis or the data we would like to analyze. For example, convolutional neural networks were based on the studies of visual cortex in mammals, and they were in particular suited in processing images. So they were using they are using the operation of the convolution in order to extract certain features from the images, like for example, shadows or edges, in order to, and more abstract information as well, in order to solve for example, classification tasks. In case of the recurrent neural networks, they were designed to work with sequential data. So whenever you were interested in the time evolution of your data, time evolution of the signal, that would be an algorithm of choice. Another interesting architecture of neural network, or a type of neural network, is called autoencoder. That's actually a network that consists of two networks. They're like mirrored. So encoder and decoder. And the goal of this algorithm is to compress your input data into this latent representation in order to, let's say, extract the key features from the data. So everything that's the most important, and later on can be used to decompress the signal, decode it into the original form with a minimal loss. You can, in principle, use this architecture to map one function into the other, and that's what I did in one of my projects. Or, for example, remove excessive amount of noise from your data. So a lot of various applications. So as any method, ANNs have certain limitations that should be considered before applying them to your data. So first and foremost, they have black box nature. We don't often know why they work in a way they do, because why by choosing certain values of weights and biases, we act, because that's what actually being changed during the training of the model. Why we receive certain results. That black box nature is under investigation as a part of a subfield of machine learning called machine learning interpretability. And because of this black box nature, they often lack the reliable uncertainty estimates. So like in the notion of certain notion of likelihood of probability is often not easy to get from neural networks. They can also be biased during the training with respect to certain features that the data have and we are not aware of. So it's really important to understand the problem you are facing with before applying this algorithm. It's powerful, it's capable of achieving really extraordinary results, but it has certain limitations. So basically that's the end of this, let's say, introductory part. That led me to the discussion of the aim of my work, the motivation, scientific motivation behind the projects I did. So first and foremost, the main, let's say, goal was to investigate machine learning as a novel method of analyzing data collected by the gravitational wave detectors. And I tried to answer, let's say, two questions associated with this investigation. First and foremost, how machine learning can be used to, let's say, study this really complex noise-dominated data, and what scientific outcomes we can get out of such applications. Because at the end of the day, that's what we are mostly interested in, not the technology itself, not the algorithm, but the science behind it. So in particular, I was interested in applying and testing those machine learning methods in the context of the signal detection. So detecting signals, for example, from binary black hole mergers, or detecting signals emitted by core collapse supernova, or those long-lasting signals emitted by non-axisymmetric neutron stars. So now I'd like to present you the 4 works, publications that at the end I decided to put in my thesis. So the first one is associated with the studies of anomalies in the data. So the paper was called Anomaly Detection in Gravitational Waves Data using Convolutional Autoencoders. The aim there was to create a machine learning pipeline that could be basically an alternative to matched filtering, because that method would not require certain knowledge about the waveforms that the machine learning requires. Additionally, since I use autoencoders, and as I said before, they are capable of kind of reconstructing the data, I thought about, let's say, considering as a part of anomaly detection also reconstruction of the signal. So where is this anomalous part in this analysis? Well, gravitational waves are actually a perfect candidate to be considered as anomalies, because according to, let's say, the definition of anomalies you can find in, let's say, signal processing, they are usually rare transient signals present in your data that are usually different from what you expect to find. For example, in this case, from the interferometer noise. Beside gravitational waves, certain glitches could also fall into this, let's say, domain. And that was good, actually, because in principle, that project could also be expanded in future toward studies of glitches, which are important for data analysis, as I said before. So the concept here was to use convolutional autoencoder and train it on the noise of the detector that sometimes also contain gravitational waves. The aim here was to reconstruct just the pure noise of the detector. Why is that? Because if the method worked as intended, then by subtracting the input from the model prediction, we could recover, for example, the signal of the gravitational wave. As presented here, though, it's just a concept. In the paper, I presented quite a few results, both for simulated data as well as on real data. But here, I would like just to briefly summarize this say real data part. So we use the O2 data, which refers to the O2 observational run. And the first part, as I said, concerns the reconstruction of the signal. So what you can see here on this blue dashed line in the background is the, let's say, original signal injected into the data, and the red one is the reconstruction. So majority of signal was lost, especially for real data. That was expected because it's really hard to analyze this data. But the merger part was reconstructed often quite well, both with respect to amplitude and the phase, which in principle could indicate that the method could later on be used, for example, for time localization. And precise time localization of signal in the data can be later on transformed into the sky localization. So once I knew that the method, at least sometimes, seems to work, the next step was associated with more like statistical analysis. So we needed to define a certain metric that would allow us in quantitative way to describe each reconstruction. As a metric, we decided to use mean squared error for the signal that I just presented. So the first step was to plot the distribution of MSE for both, let's say, studied cases of data we had. So either noise or noise with gravitational wave. Then, since those histograms, as you can see here, for all studied detectors, were kind of overlapping, we could, for example, set or analyze what's the false positive rate of this method by varying the threshold associated with the mean squared error, set it at particular value of 5%, and yeah, just use it as a detection threshold, anomaly detection threshold. Everything to the right side on those plots from those black vertical lines would be considered as anomalous event under assumption that we expect to have, let's say, a contamination of 5%. That's possible for all of those detectors. So the final tests of the method were performed on actual confirmed detection. So here is a real signal, so the very first one detected. On the left side, you can see spectrograms presenting you how it looked in the data, and on the right side, the output of our method. So to my surprise, the signal was reconstructed actually quite well. And obviously, the value of MSE for such a reconstruction was very, very high, far above those thresholds defined at previous stage, underlining that the method indeed seems to work, and we are able to pick up gravitational waves, at least associated with binary black hole mergers within the, let's say, range of parameters that we studied. The second part of my work was associated with the classification of two other types of sources of gravitational waves, so core collapse supernova and non-axisymmetric neutron star. So the first project, entitled Core Collapse Supernova Gravitational Wave Search and Deep Learning Classification, aimed to develop a pipeline based on machine learning, but not only, because we also wanted to include here an event trigger generator called wavelet detection filter that could, let's say, initially pre-classify our data in order to extract only those events in the data that are worthy of further analysis. So yeah, like the test was performed on simulated data, but based on sensitivity curves for two interferometers, Virgo, which is operating now, and the Einstein telescope, which is which is, let's say, the detector of future here in Europe, and it's supposed to be built underground. And yeah, beside gravitational waves, so core collapse supernova gravitational waves, we also included glitches here in this analysis as well. So that's just a sketch of the pipeline. We had like a raw simulated data, so certain time series applied to event trigger generator that was producing the, let's say, promising candidates events that could later on be used to train and later on classify, let's say, see the data either as gravitational wave or as a glitch. And we used two different representation, time series and spectrograms. Why is that? So as I said before, core collapse supernova gravitational waves are quite hard to, let's say, model. We don't really know how the exact waveform looks like. The supernova explosion is really complicated process to model. So there are quite a few, let's say, state-of-the-art three-dimensional advanced simulations existing nowadays. At the time of writing the paper and doing this work, we decided to use those 5 that you can see here, and they are quite different. And all of them refer to core collapse supernova. So as you can see, it's definitely non-trivial task to search for those signals in the data. However, once you start plotting the spectrograms, like time frequency representations, it turns out that there are certain similarities that those waveforms share, at least in this domain. For example, associated with G modes that appear at, so the oscillations that are present during the collapse at certain higher frequencies. And though it's really hard to see it in this representation, so the time series, but they can be present basically in those parts. And we hope that, let's say, the machine learning part of this pipeline would be able to pick up those similarities and use those features later on to classify correctly signals. So here's just a brief summary of the results we had for all, let's say, studied cases. So 1D, 2D, and ET data, as well as Virgo. This representation is called confusion matrix, and it shows, let's say, the percentage of the accuracy for a given signal. So basically, in all studied cases, we were able to achieve 97, 98, or even 99% of accuracy, which was really high overall. Additionally, we studied the response of the model we chose with respect to multi-label classification. So in this particular case, we were curious what's the response of our machine learning model with respect to particular model, core collapse supernova model. What kind of features it can extract, and how good it is in seeing differences between different models. And indeed, it was working quite well, not as good as before, but at the same time, the problem was much, much more complicated. So the third paper, with a very long title, Convolutional Neural Network Classifier for the Output of the Time Domain F-Statistic All-Sky Search for Continuous Gravitational Waves. Pretty long, but at the same time, it contains all the information about the project. So indeed, we are studying continuous gravitational waves emitted by those non-axisymmetric neutron stars. We use the convolutional neural network, but again, not to work with the raw data as in the case of the first project, but similarly as before, to combine it with certain pipeline that was producing already, let's say, the promising candidates called TDF-STAT. So we, beside the gravitational waves, we are also considering the, let's say, application of this method in the studies of stationary lines, which are quite like something like glitches, but for this type of studies, because those noise sources are persistent all the time. An example of stationary line might be like a frequency associated with the current in like electric cables we use. It's either 50 or 60 hertz, for example. So TDF-STAT on its own is a mass filtering algorithm that is quite complicated. It consists of few parts. So the first step is to, let's say, analyze the raw data, so the time series, demodulate the signal, because this modulation that you can see here on this, by this, like, red color, is associated with the motion of the Earth with respect to the barycenter of the solar system, as well as the rotation of the planet itself. So once the signal is demodulated, it can be converted to Fourier transform, and then the search might be performed on a certain grid of parameters: frequency, spin down, so the derivative of frequency, and the points or the coordinates on the sky, declination and right ascension. And since we have this grid of parameters in the multidimensional space, what we end up are those distributions of the signal candidates. Each point corresponds to one signal candidate associated with those 4 initial parameters and the result of the search of the F statistic, which returns the signal to noise ratio for this given candidate. So the idea was here to stick with those representations and consider the project as an alternative to what's called coincidence studies, because since continuous gravitational waves, as name suggests, are quite persistent in time, what's usually done is we split the data into a few consecutive time segments, for example, 2 days, 6 days, 24 days, and so on. We run this analysis and we perform, let's say, the coincidence studies on the consecutive candidates, which is quite computationally heavy as well. So the idea would be here to kind of replace this part of the pipeline. So we chose those those representations, so this multidimensional distribution of signal candidates, converted into 2 different representations that could, let's say, present different features. For example, 2-dimensional histograms. The color here refers to the density of points on the previous in the previous plots, and use those as, let's say, image representation. Then there was like a vector representation with just a peak of the, let's say, the F statistic SNR, 50 maximum values and their corresponding parameters. So we studied, let's say, the potential of this method in quite a few cases, but to give you just a brief summary how the method worked for gravitational waves, so the most interesting part. So you can see here how the accuracy of the detection changes with respect to the signal SNR, as well as different frequencies that the search was performed for. So for the 1D case, obviously the results are much better and much more consistent than for 2D case. Then we performed something referred to as generalization studies, because we performed similar search, but on frequencies that were not used previously during the, let's say, the training of the algorithm. So just to see if our method is actually capable of generalizing the problem towards more generous case when we don't actually know the frequency of the signal we are looking for. And the last project was associated with the rather with the problem of regression than classification. So the project entitled Neural Network Reconstruction of the Dense Matter Equation of State derives from the parameters of neutron stars. So the idea here was to apply an autoencoder to inverse the Tolman-Oppenheimer-Volkoff equations to say something about the equation of state based on neutron star observables such as masses, radii, or tidal deformabilities, and to study various aspects of this analysis associated, for example, with different number of observations, varying like errors of observations as well. So what's usually done in this type of analysis is you have certain assumed equation of state. So the relation between pressure and density, for example, you solve Tolman-Oppenheimer-Volkoff equations, and what you end up with is a theoretical mass-radius relation, for example, for a given equation of state. Then you can compare those theoretical relations with actual observations. Because of those uncertainties in measurements, let's say the conclusions of such an analysis would be ambiguous. So sometimes in principle could be possible to reverse the project. So use actual observations and reconstruct equation of state. But then again, because of uncertainties and because we cannot actually probe in details whole, let's say, mass radius parametric space, but we just have like random observations more or less, it's really hard to actually say something about the equation of state. This approach. So our idea was to introduce an alternative. So use an autoencoder to convert this representation, so on the left side to the right side. So as you can see here, there are 2 populations of observations, blue ones with larger initial measurement uncertainties, the red ones with much, much smaller. But in both cases, the reconstructed equation of state, so on the right side, were quite precise. As for the bottom plots, they are referring to the observables that we can have from gravitational wave observations. So mass and tidal deformability. And tidal deformability we used at the end in the project was not in, let's say, the original units. but rather as a converted value, which we called like tidal radius. Because the advantage of this approach was the same units. Just for the comparison purposes, we could basically use this error with hat and compare both approaches. So final test of this method was performed on astrophysical equations of state, because the training and the results, as I showed you before, refer to relativistic polydropes, which are, say, simple mathematical models that might describe equation of state, but there is no actual astrophysics behind them. So we chose 3 models, SLY4, APR, and BSK, to actually check how well the method will work, because there is some actual science behind them, and they were a bit different from those before. So that was, in a sense, also a test of generalization capabilities of the method. And again, for example, those are results for the highest uncertainties of those we studied, so considered in the paper. Overall, the results were quite correct. Well, this area around the high pressures and densities was not reconstructed as precise as one would like. Also because to probe this region, you need quite a lot of observations associated, for example, with high masses. And because of neutron star mass function we used, we did not really have many, let's say, samples from this region. So obviously the uncertainty or error associated with this high pressure density was expected. So basically that's it. Well, in my research, I wanted to show that artificial neural networks and in general machine learning is capable of doing of solving a lot of potential problems you might face in gravitational wave astronomy. So first and foremost, it can be used to search for various types of gravitational waves. Also, it's capable of let's say, distinguishing those signals, astrophysical signals, from glitches, which is a certain limitation for other methods used even now in official pipelines of data analysis. So basically, that's it as for the presentation. Thank you very much.
Thank you. Okay, so this thesis has been scrutinized by 2 reviewers who are Professor Franco Bertone of Amsterdam and Dr. Habitowana Katarzyna Małek of the National Center for Narodowe Centrum Badań Jądrowych. Okay, so I would like first to ask Dr. Habitowana Katarzyna Małek to present her review.
Thank you very much. Can you hear me well?
Yes.
Okay. So I would like to present my report, which is a bit extended. So maybe I will try to shorten it a bit, as we already had a very good introduction from Michał Bejger and Elena Kłoko, if I describe it well. So yes, so the PhD thesis of Mr. Philip Morawski, written under the supervision of Professor Michał Bejger and Dr. Elena Kłoko, describes an original work related to the analysis of the data collected by the gravitational wave detectors using machine learning. More specifically, the PhD candidate used machine learning to detect and reconstruct the gravitational wave signals. He investigated various aspects of gravitational wave astronomy, both already detected types of compact binary coalescence system using a novel approach for searching for anomalies in the data, and previously undetected system as such core collapse supernova explosions and oscillating, rotating, isolated neutron stars. Mr. Morawski also investigated the possibility of reconstructing neutron stars' physical parameters from a gravitational electromagnetic multi-messenger perspective using machine learning algorithms. In his thesis, Mr. Morawski presented an excellent efficiency of artificial neural networks in hunting and reconstructing different types of gravitational wave signals. The thesis is written in English and consists of 6 chapters, including a complete introduction to the subject. Okay, then maybe I will skip some very detailed part and I will go directly to the description of the work and the main results. The introduction contains a very detailed presentation on the topic of the gravitational wave and machine learning techniques. This part demonstrates that Mr. Morawski can very clearly and in a very deductive way present complicated interdisciplinary knowledge that he used to finalize his thesis. In the second chapter, he presents how gravitational wave detection can benefit in the future from autoencoded based anomaly detection. In that work, gravitational waves are defined as anomalies in the data and originate only from the binary black hole system mergers. Using artificial neutral network algorithms, authors of the paper were capable of detecting those anomalies after training or either simulated or the real data. In the second part, the third chapter of the thesis, he described a search and classification procedure from gravitational waves from previously undetected core collapse supernova explosions. For this purpose, a convolution neutral network combined with an event trigger generator was used. To test the accuracy of the CNN classification, the 5 hydrodynamical simulation of neutrino-driven core collapse with different zero-H main sequence were used. To simulate Gaussian noise for Virgo O3 run and the future Einstein telescope. In the fourth paper, the fourth chapter, the paper 3, he describes work that naturally follows the previous paper. In this work, Mr. Morawski was searching for a gravitational wave signal in oscillating, relating isolated neutron stars. Again, he used the CNN algorithm to classify gravitational wave signals candidates related to the continuous signal emission by the form rotating neutron stars. The novel approach presented in this paper is adopting signal candidates as the deep learning input instead of raw data. Moreover, using the time domain F statistic increases the significance of possible astrophysical signal detections. In the fourth paper, the chapter 5 of his thesis, he shows the possibility to reconstruct the neutron star equation of state based on the electromagnetic information like masses and radii and or the gravitational wave signals with the information from component masses, tidal deformability during the system in spiral. And Mr. Morawski concludes in this paper that the ANN algorithm can be successfully applied in the precise reconstruction of the dense matter equation. The detailed analysis showed that the realistic distribution of the parameter based on presently known observation is insufficient for a detailed reconstruction of the equation of state. To overcome this problem, many observations of massive stars are required. Also, the future telescopes and detectors as for example, the Einstein telescope, which characterizing much smaller measurement can be used for the previous analysis. The chapter 6, the last chapter of the thesis and also the shortest one, consists of the summary and outlook. It was a bit disappointed at this part. I was expecting an extensive summary of all 4 papers. But to conclude, the reviewed doctoral dissertation is a comprehensive study whose undoubted achievements and the successful implementation of machine and deep learning technique to look for the gravitational wave signals in a very noisy data and how to use the reconstructed signals for scientific analysis. What is also stressed by Mr. Morawski is the bright future for artificial neutral network in the gravitational astronomy, even to the black box nature of this method. The thesis is written in a very good English. I would like to say that all 4 articles presented in this thesis are already cited in different scientific journals. All publications have a very comprehensive and complete introduction. And here's some comments. In my impression, the description of papers used as a separate chapters is too short. I would expect a kind of storytelling to show how different papers are connected and how they build a homogeneous whole, especially as the dissertation has a form of a collection of articles. In total, 1.5 pages can hardly create a necessary justification why Mr. Morawski chose this form of dissertation. From my perspective, the detailed physical understanding of the process is more important than the test of artificial neutral network performed of different samples. From used articles, it is evident that all tests were done to improve the gravitational wave signal analysis, but from the last 2 pages of the introduction, one can have an impression that it is more about the machine learning and less about the physics of astrophysical objects. In my opinion, one paragraph or appendix is missing in paper 1, which would describe the specific choice for physical parameters used for the electromagnetic simulations of the signal emitted by a binary black hole system. The author used both masses and initial mass functions compatible with the first GW 1509-14, but not GW 1706-08 or GW 1708-14. I think that the additional analysis should prove this choice. I am also missing a paragraph to compare obtained results with additional simulation compatible with both gravitational waves, or only with the second or third. It was also not written what the relatively strong signal of the gravitational wave detection means and why only those 3 events were chosen for the test. The next comment is what I found. I found information about the accuracy and efficiency of all the ANN method in all presented papers, but not about the contamination. In paper 2, an excellent total accuracy is shown, similar to paper 3. In my opinion, contamination defined as the ratio of misclassified signals and the total number of signals classified by artificial neutral network as gravitational wave signal is also an important factor determining the method usefulness. To summarize this comment, I'm missing a dedicated discussion on the purity of the final classification. There is also no description of the alpha parameter from ADM optimizer. In paper 1, alpha parameter is equal to 0.0005, while in the second and the fourth one, alpha is equal to 0.001. Why are those numbers so different between articles, and what does it mean for the final results? I was surprised reading paper 1 and 2 that the model validation in the deep learning pipeline was done using only for 10% of the data set. Wasn't it too small to create a final conclusion? And paper 3 used 20% of the data sets to validate the result, which sounds more reasonable for me. More surprisingly, there is no validation sample in paper 4. Why it's so? Maybe I was missing something from the paper. And minor comments, I don't know, should I also read the minor comments? Okay, maybe I will. So I would suggest to use a different style of references, like name and the year of the publication instead of numbers, because it makes reading more demanding. And in my opinion, this desideration misses a table with all abbreviation used in the text and the attached articles. The thesis consists of acronyms related to gravitational wave astronomy, statistic, and machine learning technique. And the number of used abbreviation is large, and the thesis would benefit a lot from such a table. In the introduction in paper 1, some figures are presented in a slightly tidy way. So, for example, lack of scale of axis description, and yeah, so this is very detailed. I think I don't need to read it now. Paper 2, I couldn't find a description in the text for figure 4, but maybe also I did something wrong. In the paper 3, in the summary, it is written, this project is one of the few that research the application of deep learning as a supplementary component to MF, and what the MF stands for in this sentence, because I also couldn't find it. But all the comments presented above do not diminish the value of the work of Mr. Morawski. In my opinion, submitted desideration provides new valuable input to the area of gravitational wave astronomy. The thesis written by Mr. Morawski constitutes our original solution to the scientific problem of detecting and reconstructing gravitational wave signals. Presented introduction as well as published articles undoubtedly shows that Mr. Morawski has good and solid knowledge in the area of machine learning application and the data analysis of gravitational wave detectors data analysis. 3 first author papers and 1 second author paper also shows the PhD candidate's ability to independently conduct scientific work. Summing up, I consider the doctoral thesis of Mr. Filip Morawski to be a valuable contribution and to meet the criteria prescribed by the law for a doctoral desideration. Therefore, I request that this desideration be admitted to public defense, which is done now. Thank you.
Thank you. Let's ask if we have Professor Bertone with us. I don't hear. So in this case, I assume Professor is not present, and I will read his review in full. So this is the the review by Professor Bertone. It's dated January 18th, 2022. To whom it may concern, it is a pleasure for me to review the dissertation submitted by Philip Morawski. The document is structured as follows: an introductory chapter, 3 chapters consisting of 4 published papers, and a final outlook section. The introductory chapter offers a rapid introduction to the themes discussed in the paper, in particular gravitational waves and machine learning. The text is always very clear, and it demonstrates the candidate's general theoretical knowledge in both disciplines. The reference to the literature adequate to its scope. The main contributions of the candidate are discussed in the 3 following chapters. The common thread among them is the potential of machine learning for detecting gravitational waves, with a particular emphasis on the detection signals as anomalies in the data. In terms of the fundamental questions answered, the focus is on the detection of signals emitted during supernova explosions and by non-axisymmetric neutron stars, and on the reconstruction of the fundamental properties of neutron stars. The paper, titled Anomaly Detection in Gravitational Wave Data Using Convolutional Autoencoders, included in Chapter 2, explores the application of convolutional autoencoders to gravitational wave data. The method is trained on both simulated and real detector data, and the anomaly searches in time series there are convincingly validated on real data containing confirmed gravitational wave detections. In papers 2 and 3, contained in Chapter 3, the candidate explore the application of convolutional neural networks to the search for core collapse supernova and deformed neutron stars. This pair of paper contains several interesting results. Spectrograms, for instance, are found to be significantly better representations than time series. As the evolution of signal frequencies helps distinguish gravitational waves from noise, the method appears to offer a robust classification of the signals and to be able in particular to discriminate between astrophysical signals and detector artifacts. Paper 4, finally, demonstrates that neural networks with an autoencoder architecture are able to learn and generalize the mapping between the measured parameters and the fundamental equation of state describing the state of the matter inside neutron stars. Morawski's dissertation is interesting and timely. In fact, it could not have come at a better time, as it explores the interface between gravitational waves and machine learning, at a time when both disciplines are quite literally booming. The results contained in the scientific papers are clearly original and based on the declarations of the co-authors, largely led by the candidate, which clearly demonstrates his ability to independently conduct scientific work. In view of all of this, I consider the doctoral thesis of Philip Morawski to be a valuable contribution and to meet the criteria prescribed by the law for a doctoral dissertation. Therefore, I request that this dissertation be admitted to a public defense. Sincerely, Gianfranco Bertone. Okay, so now it's time to present his response to the reviews.
Okay, thank you. Okay, so as for the comments of Professor Kaczmarek, so I allowed myself to split some of them in parts because some of them are quite long. So on the blue, you can see the original comment, and the black one is my answer, which I also gonna summarize. So the first comment was about the the first part of the first comment indeed was about the let's say character of my thesis, which indeed might seem to the reader as non-homogeneous with papers that I just presented as loosely connected one with another. So yeah, so indeed it might seem so, but at the same time, from my point of view, it starts to make sense once you include, let's say, the character of the thesis, its aim. So it's a kind of exploratory character. So yeah, so indeed, since like all of those works were kind of like proof of concept, and definitely they had this exploratory character, machine learning was serving as a link between all of them. So that's something that connects all of them, in particular artificial neural networks. Though I can add here that, as Michał suggested at the mentioned at the very beginning, the idea behind my thesis at the very beginning was to carry out 4 research projects associated with different types of sources of gravitational waves. At the end, I managed to put in the thesis three of them, though like I also did some research on stochastic background, which is published. But I additionally also added this paper associated with the reconstruction of the astrophysical parameters. So on the example of equation of state, which I believed only enriched the overall quality of the work. And what I can add here, I believe that in a sense, my thesis resembles the character of the gravitational wave astronomy, which is quite non-homogeneous if you can think about it. Because on the one side, we have signal detection. On the other hand, we have certain parameter estimations. Also, we can study the detector itself as a part of this domain. For example, to learn something about the glitches, try to eliminate them from data. So yeah, so that's basically it, what I can say about this comment. So I wonder if Professor Kaczmarek wants to say something on this part.
Yes, thank you very much for this explanation. In my opinion, I just missed some description in the thesis itself, which explain that. Not that those papers are not connected, but I would really expect a little bit longer description why those papers want those subjects. But thank you very much. It really, I really appreciate your answer. Thank you.
So I agree. Like from perspective, it seems that I could elaborate more on this aspect because yeah, that's actually very important as for the motivation itself. So the second part of the first comment, yeah. So a few words about the, let's say, astrophysical motivation. So as I said during the presentation, indeed, let's say the motivation on the scientific side, the motivation was associated with the tests of the methods like artificial neural networks on the signal detection associated with different sources of gravitational waves. So, but at the same time, stating that would be a sole purpose, I would not agree with this because artificial neural networks or machine learning in general is quite a new domain when it comes to like applications to this type of problems in astrophysics. So I believe that first we need to actually understand them, and then yes, the second step is to actually try to improve the results as much as possible once we will understand, especially this kind of like black box nature of neural networks. So as of now, the works that I presented, indeed they are proof of concept. So the next step would be actually to improve the results presented there, which I believe it's definitely possible. Okay, so the comment number 2. So yeah, like I'm not sure what the electromagnetic simulation refers to. I guess it's about the simulations actually about the gravitational waves emitted by the binary black hole merger. So as for the motivation, well, first and foremost, we wanted to have transient signals shorter than 1 second in the sensitivity range of the detector. So 20 solar masses or 20 few solar masses was below this value was actually excluded. We also did not want to cover whole parametric space of masses because well, we wanted also to test generalization capability of the model. So if we include as a part of the test of the training whole parametric space, then that wouldn't be actually possible. So maybe let me also address those two parts of this comment. So those three events were chose as during the at the stage of writing the paper. Only gravitational wave catalog number 1 was present with those 10 or something events, and those were the strongest ones in terms of optimal SNR. It was important for us because relatively strong means that it can be, let's say, picked up by the method, because from the previous stages of the analysis, we knew that everything, let's say, below 8 to 10 of SNR for a single interferometer would not be detected by the method. So we wouldn't not test basically anything. So that's what I can answer here. And as for the last comment about this comparison with additional simulations compatible with both gravitational waves, well, I believe that such studies are worthy of a separate research. And actually, I guess I mentioned in the conclusion of this paper that I would like to do this in the future, to study the effect that the various masses of black holes, for example, might have on the performance of the model. So that's it on the second comment. Okay. So yeah, like comment number 3, I agree with the referee. The contamination is very important and should be included as a part of the analysis. And we also did it, though it's not presented in the work, as it not really added particular value to the conclusion of results. And also, I believe that adding too many numbers, and like that paper was already full of results, would make actually harder to understand what was going on there. Maybe that could be added in appendices. I agree, but in general, that's what we decided to stick with, the most important results to be put in this particular paper. So comment number 4, the alpha parameter is also called learning rate. And it determines how much to change the model in response to the estimated error of the cost function, which defines the error of the neural network. Each time the model parameters are weights and biases are updated. So it simply refers to the gradient descent, which is an optimizer used to train the neural network. So basically, imagine that we have a certain error function that defines how good predictions of the model are. So what the gradient descent does, it tries to find the global minima, usually, of this function. So we can use a comparison with, let's say, 2-dimensional case. So we have one weight, one bias, and the value of the cost function, which is the function of those parameters. And what the method does, it's that we start from the, let's say, the certain peak on this, like, let's say, mountainous range, and we try to go all the way down to the valley. And learning rate will refer to the, let's say, steps that the gradient descent does during each iteration. The smaller it is, let's say, the finer the motion, but at the same time, it can get stuck sometimes. The larger it is, let's say, the training might be harder to actually find the global minimum. And as for the comparison between, let's say, various values of learning rates between papers, it's actually quite hard to compare those parameters because they are problem specific and they refer to particular architecture and the data we have. So we could, in principle, compare it, but to be honest, I'm not sure what one could get out of such comparison because those are totally different problems. So comment number 5. So validation sets described in all of the papers were used to examine just the learning curve. So this refers to the way that algorithm learns, whether it learns correctly. Final conclusions are associated with test sets. And as for the last paper, so that's actually my mistake. So thank you for pointing this out. I wasn't aware that I did not add it in the paper, but of course, validation was there as a part of the training data, which was also described in the paper. The values or the sizes of those sets, well, it's again problem specific. If you have a lot of data, you can make this set larger. If it's like well balanced or like unbalanced, so for example, it's dominated by certain cases in your data, then it's, let's say, more complicated to design a validation set that would be statistically representative with respect to the problem posed. But yeah, again, it's one of the things that you actually specify for a problem and the data you have. So sometimes this number is smaller, sometimes it's larger. I guess there is no like golden rule here. So the minor comments of this editorial nature. So Well, I agree with the referee that certain things could be improved. For example, like the reference format. Indeed, since the thesis was quite long, changing the reference format could actually help the reader. The same with table of abbreviations. Yeah, unfortunately, I did not add it to the paper, and like looking from perspective, it definitely should be there because of the amount of abbreviations and the information presented. Yeah, the comment number 3, so that certain figures in one of the papers are not of the best quality. Well, at the time of writing, I hope that they are like kind of self-explanatory. It turned out that with time, actually, they were not as descriptive as I hoped for. So indeed, that thing could also be improved. So thank you for pointing this out. As for the comment number 4, so yeah, like I checked, and the reference to the figure was not added, even though the description was there. So it was about the actual, like the figure presented glitches, if I am correct, models that we included in the data. And the last comment, so like MF refers to matched filtering. So it was described as a part of the paper, but yeah, it wasn't introduced before. So just an editorial issue. So that's all for the comments.
Thank you very much for all the explanation. Now I think that I'm fine with all your answers. Thank you.
Yeah, thank you indeed. Now will be time for questions. Can we list the participants? So if you like to ask a question and you are on Zoom, please raise your hand. If you would like to ask a question here in the room, please line up to the microphone here. So tego to było na bocznym panelu, to coś widać. Okay, Anka, please.
Thank you for this excellent presentation. My question would be, in terms of machine learning, do you want to achieve accuracy better, or you want to make your code faster? So which one, or is there any trade-off between these two?
Well, the speed usually does not really matter as long as, let's say, you have decent hardware, for example, on GPUs or even dedicated hardwares. That's once trained, the models are fast, because in principle, artificial neural networks are just like multiplying certain matrices on your data that you provide. So that's it. So it's super fast. And usually the speed of computation, it's not an actual challenge in majority of cases. Accuracy, yes, it is important, and most likely accuracy in terms of, let's say, reproducible results. Because as I mentioned before, like artificial neural networks sometimes lack this reliable uncertainty estimates. So it's great that, you know, your model works on the data you have, maybe on future data, but the question is if in 5 years from now on, they will still work the same way. So addressing this issue is of the utmost importance, because like to have a reliable method, because especially for gravitational wave studies, we need to have reliable estimates, because those classical methods are providing you certain notion of like likelihood of probability. So yes, that's, I guess, the main goal there.
Okay.
Yeah.
Thank you.
Thank you.
Other questions? It's Agnieszka Janiuk, I think.
Hello, I'm on Zoom, but I hope you can hear me.
Yes.
So my question is about this collapsing star. Where is the origin? What is the origin of a gravitational wave? Can you say some more details about this process? Where do the gravitational waves originate in the collapsing star? And then if we are able to detect this wave, can we infer some information from the shape of this gravitational wave about the properties, physical properties of the star?
Yes. So let me think for a moment. Yes. So as I mentioned before, one of the criterion to emit gravitational waves, it's the non-axis spherical symmetry, the lack of axis symmetry. Maybe I can put it this way, which is also associated with the let's say the quadrupole emission, or the time varying quadrupole emission of the mass distribution. And yeah, like during the collapse, because as I imagined it, it's quite a violent dynamic process. So certain, let's say, fluctuations in various parts of the star might occur, leading to the breaking this axis symmetry, which further leads to the time varying quadrupole momentum. So as I believe, because of how dynamic the process it is, in a sense stochastic, I expect to have a certain degree of this non-axis symmetry, the degree of which is, I believe, not known, and various models of core collapse supernova explosions, as far as I remember, are using, let's say, different values of this amount. And as for the detection of the actual signal, yes, so especially what I said before about this time frequency map, it is expected that there are certain features associated with actual physical phenomena. So as I said before, for example, G modes at higher frequencies, or also SASI, which stands for the standing accretion shock instability, and maybe potentially something else. So I believe that in principle, yes, by actual detection of those types of gravitational waves of certain types, we can actually learn something about what's happening during those events, and those informations probably are only accessible by gravitational waves, because light does not allow us to see actually what's happening inside there. That's what I can say.
Okay, maybe one additional question. I will try to help you, because I'm interested in the main property of the star, for instance, its rotation. So does the degree of rotation of this massive star influence the possibility and the shape of the gravitational wave, and how is it formed?
Probably yes. Probably yes. To which degree, to be honest, I don't know. Yes, as I believe, since we might have differential rotation during this event, so outer parts of the star might move certain different velocity than the inner parts, and when everything actually is collapsing and it's also rotating, then yeah, as I imagine this might cause the appearance of certain non-spherical appearance of some non-spherical aspects of this phenomenon.
And what is non-spherical actually in the core of the star?
The mass distribution itself, rotating mass distribution, or it's not maybe non-spherical, it's non-axis symmetrical, maybe like this.
Yeah, okay, I meant just the protoneutron star.
What exactly? Matter, so at that stage should be some degenerate matter full of most likely iron atoms, definitely, that are photodisintegrated by gamma rays being produced as a result of the collapse. So probably quite a few different particles, starting from the iron, which is being disintegrated into lesser atoms, nuclei, as well as just neutrons or protons. That would be my guess.
Okay, thank you very much. Thank you.
Thank you. Anybody will, David?
Hi, Philip. Great presentation. I just had a minor question about gravitational waves themselves. Is there a gravitational analog to opacity, basically, for gravitational waves? Because, like, basically, in another way, does the gravitational wave is emitted and it, travels through the universe and through mass and stuff? Does the signal get, distorted by the mass that it passes through, or does it, arrive intact?
So I heard about the gravitational wave lenses. In principle, that signal might also be lens. I don't know if it's exactly refers to the opacity, but definitely it is possible to lens gravitational wave. I don't know much, to be honest, about this. I just heard 1 or 2 presentations in my life about this issue, but yes, this way they can be, let's say, affected. But in terms of opacity, well, question is for example, a gravitational wave passing through a black hole, like a lens. Yeah, it's part of the signal might be lens, and probably the one that enters black holes, probably not anymore. So yeah, nothing else comes to my mind. Because usual matter should not, because it's not interacting as much as electromagnetic waves indeed.
Okay, I see a raised hand by Dorota on Zoom. Who is it?
Yes, Dorota Rosińska. Hi, Filip. My congratulations for very nice work and great talk. I would like to come back to the question, maybe not by Agnieszka, but concerning core collapse. I wonder what kind of models you were using to use machine learning, because this is really a very big problem, because we have really quite different models depending on the masses of progenitor, depending on magnetic field, depending on rotation, and depending on the degree of differential rotation. So I just wanted to know if you just decided to use some particular models which has something common, for example, the mass of the progenitor, yes, and weak magnetic field or something like that.
Okay, yes, so the models that you can see now on the slides that we used are from the 3-dimensional magneto-hydrodynamical simulations, all of them. And as I believe, they all include the neutrino transport as a mechanism, basically taking a part, like an active part in actual supernova explosions. The exact details between all of them, to be honest, I don't necessarily remember. I know that some of those models were not actually, let's say, bursting at the end. Yes. So
those models were coming from one particular team, yes?
No. So there were three teams actually that made those models.
Yeah, because I think that for machine learning, you will feel more comfortable if you have something similar, not quite different. But okay, it was just
not necessarily, because in this particular case, well, all the models that you can find, there are 30 few of them, if I'm correct, like those 3-dimensional, so more advanced, are quite different. For example, this S25, so the middle one, has certain weird. It has certain weird feature that it just ends. And why does it end? It's not because of any, let's say, physical phenomenon occurring there. It's just the end of simulation. Those simulations are really heavy, like they are performed on cluster and last for half of the year, for example. So it takes really a long time to get any out of those, any model for any, let's say, set of initial parameters. And the thing is that we don't really know exactly, let's say, which out of those models might be better to study supernova. So time series representation most likely is not the best approach to learn about it, because how different they are. But in time frequency maps, those certain features like the SASI or like G modes or something else, if possible, if it was included as a part of those simulations, should be present. And probably time frequency analysis in general is a way to go to detect those signals in future. So that's what
I agree with you that it would be much, I think, easier. Okay, thank you very much.
Thank you. Please.
I just wanted to comment that it is actually quite difficult to get a kind of uniform sample of such simulations. They are basically kind of handpicked from various groups, because this is really a costly computation. We are probably not there yet to have a very nice big uniform sample with everything, all the masses, all the parameters tested in all the ways that we want. So that is an additional difficulty.
Yes, I agree. Yes, indeed.
Okay, thank you. So I don't see any other raised hands, so I will stop the discussion at this point. And now I will ask members of the Scientific Council to switch to the Council Zoom meeting. And the others, please wait several minutes. Okay, I'll announce this in Polish. So, jest mi niezmiernie miło poinformować Cię, Filipie, że Rada Naukowa CAMK podjęła uchwały o przyjęciu Twojej obrony, a także o nadaniu Tobie stopnia doktora. Gratuluję.
Dziękuję.
I poproszę teraz Michała Biegera o przyjęcie ślubowania. Trzeba włączyć.
Hello? Okay, so I will read the text in Polish. Szanowny doktorancie, stajesz dziś przed nami, by po przedstawieniu rozprawy i zdaniu egzaminów, w których wykazałeś wymagany poziom wiedzy i umiejętności, uzyskać stopień doktora nauk ścisłych i przyrodniczych. Przyrzeknij zatem, że wiedzę swą tu zdobytą wykorzystywać będziesz zawsze dla poznania prawdy, prawdę tę będziesz głosił i nią kierował się w życiu. Przyrzeknij także, że zawsze będziesz wytrwale pracował dla rozwoju nauki, a jej wyników będziesz używał nie dla niegodnych zysków i próżnej sławy, lecz dla dobra powszechnego. Przyrzeknij również, że swoim zachowaniem nie splamisz godności, którą ci mamy nadać. Czy przyrzekasz?
Tak, przyrzekam uroczyście.
Na mocy uchwały Rady Naukowej Centrum Astronomicznego imienia Mikołaja Kopernika Polskiej Akademii Nauk, ja, wyznaczony przez nią promotor, mianuję Ciebie, Filipie Morawski, doktorem i przyznaję Ci wszelkie prawa i przywileje przysługujące doktorowi.
Dziękuję bardzo.
Gratuluję.
Dzięki wielkie.
Nie ma dyplomu, a uprzejmie wręczam Ci ten dyplom, to, że nie masz dyplomu. Gratulacje.
Dzięki wielkie. Dobra.
To będzie wręczony w swoim czasie. Tak.
Proszę członków Rady Naukowej o przełączenie się na Zoom, na spotkanie dla członków Rady.
Gratulacje wielkie.
Ja też jeszcze skorzystam z okazji. Gratulacje.
Congratulations, Philip.
Uh,